Today we are joined by Serena Vinciguerra, who is here. She actually works on a lot of very broad topics, mostly about gravitational waves and neutron stars. Serena obtained her master's at the University of Trento, and after that continued to obtain her PhD from the University of Birmingham through a very highly competitive Marie Curie initial training network called Graviton. She has worked on gravitational wave burst algorithms, parameter estimation, and the Supremo algorithm, for those who know. And she also was an active member of LIGO in the time. She then did a combined postdoc at the Max Planck Institute in Germany, as well as Monash in Melbourne, where she mostly worked on stellar evolutions and simulation of gravitational wave sources and X-ray binaries. And she's currently working in Amsterdam on neutron stars and nicer data. So please welcome Serena and yeah, enjoy her talk. Oh, and by the way, she's super active in outreach, and she also is a pretty good artist. And so many of the animations that you'll see today are actually drawn by herself. Yeah, good luck.
Thank you, Flora, for the nice introduction, and good afternoon, everybody. And really thank you, everybody, for having invited me here to talk about my project on Be Xray binaries. So the main goal of this project is to actually learn something about binary evolution by comparing observations of Be Xray binaries with predictions. And in this work, predictions will come from the population synthesis code COMPASS, of which Flora Bruchharden here is one of the main developers. But if you don't know anything about population synthesis code, don't worry, because later on I will give a brief overview of what are the key points which are relevant for this project. But let me start with in a slightly unconventional way by sharing with you what I recently learned. So apparently it has been proven that it is easier to capture the attention of the people in the audience if the speaker shares something personal with them. So let me go through very quickly, answer to 3 questions that might cross your mind throughout the talk. So first of all, yes, as you probably have already guessed, I am Italian. Actually, I come from a very small village, but a very big family in the north of Italy. And yes, the female character you'll see here and there throughout the presentation is supposed to be me. But most importantly, yes, I really do have for real a pair of different, very colorful shoes, in the case you managed to see them throughout the talk. But now let's go back to what is the main point of this talk, which are Be Xray binaries as for constraining binary evolutions. And if you're already asking yourself, why should I care? Well, I believe that really in astrophysics, there are only few topics that are not touched at all by binaries. For example, if you are working on massive stars, you should understand binaries because massive stars are very often found in multiple systems. If you study supernovae, you might also need to account for binary interaction, whether you're studying supernovae type 1a, where you need a binary companion for the supernovae to occur, or whether you are actually studying more into details the supernova mechanism, which might be related to the property of the progenitors, which themselves are subjected by binary interactions. And of course, nowadays, binary evolution is very popular for explaining the merger of compact binaries that we see through gravitational waves and the associated electromagnetic emissions. But actually, binaries are per se very interesting systems and can generate transient in several frequencies. For example, short gamma ray burst or X-ray in X-ray binaries. And actually, before the nicer announcement of last year, binaries were the only means that we had to measure masses and radius of neutron stars, and so to probe the neutron star equation of state. Binary interactions are also important for understanding nucleosynthesis. For example, to account for the enrichment of the environment due to mergers of double neutron star, or the winds of massive star or supernovae, etc. And binaries are also important, for example, to correctly infer star formation rate from UV spectra from faraway galaxies. And I could keep going on in this way. So hopefully I by now have convinced you that binary evolution is important. Okay, but of course, life would be quite boring if we would have already figured out everything about it. So there are actually many open questions in the field that people are currently investigating. And here I reported some of the main challenges of the field. For example, we still need to reach a coherent understanding of chemical evolution, homogeneous evolution, and more in general on how to treat the effect of rotation in both stellar and binary evolution. We also need a better understanding on natal kick distributions for compact objects. And in terms of mass transfer, we need a better understanding on how to probe stability criteria and a better understanding of the physics that goes into common envelope, for example. And even though you might not have heard much about that, there are also quite important uncertainties concerning stable mass transfer. And in particular, this talk will focus on the accretion efficiency, which is one of the parameters that can describe stable mass transfer. And it refers to the fraction of the mass which is lost by the donor during mass transfer, which is actually accreted by the companion. And so in this very wide framework where there are a lot of possible observation and a lot of ingredients which are correlated one to another, rapid population synthesis code really can play a fundamental role and offer quite a natural way to actually combine different observations altogether. So let me say that indeed, despite the many possibilities that we have and the many parameters that are in place, by matching prediction with observation using population synthesis code, we can still learn a lot. Okay, so let me now go through the rest of my talk and the overview of that. So I will start with an introduction on Be Xray binaries. So what are them and their main properties, especially focusing on the Small Magellanic Cloud. I will then go through the core of the project while explaining some key feature of COMPASS and how we select the system to compare against observations. I will tell you what we can learn in terms of formation channels and by comparing observed and predicted distribution of properties such as masses and orbital period. Finally, I will highlight what are the main messages of this project, and I will hint to some interesting points and caveats if you want. Okay, so let's start describing what are X-ray binaries. So X-ray binaries are binaries composed by a compact object which accrete some matter and so emit X-ray from a normal star. And with normal here, I really mean not a compact object. So the compact object can be a white dwarf, a neutron star, a black hole, and X-ray binary can actually be divided in two subclasses depending on the mass of the non-compact object star in the binary. So if the companion of the compact object is a high mass star, then we have high mass X-ray binaries. And if it is instead a low mass star, we have low mass X-ray binaries. And as you see here, these two classes are actually characterized by quite different properties. And if I look, and hereafter, we are going to look mostly at high mass X-ray binaries, which are characterized by companion to the compact object, which is of high temperature, so spectral type classically or B. masses above 8 solar masses, and period between 10 and hundreds of days. And differently from low mass X-ray binaries, in high mass X-ray binary, we have that the accretion into the compact object happens through winds. High mass X-ray binary can themselves further be divided in two subclasses depending on the type of the companion to the compact objects. So if the companion of the compact object is a supergiant, we have supergiant X-ray binaries. And if instead the companion of the compact object is a Bstar, then we have BeXRay binaries. So what are Bstars? Bstar take their name from the most common spectral type that appears in these stars, which is B. And the E comes instead from the typical emission lines that describes these stars. And so going back to actually what are B stars? So B stars are classified as main sequence stars, which have O, B, or early A spectral type, and are characterized by this very rapid rotation, which is strongly correlated to the presence of a accretion disk, which we detect through this emission line that I mentioned before. And so here, this property actually, they altogether, they specifically actually the main sequence and the spectral types, that determine a mass of B star, which ranges between 3 and 25/30 solar masses. And hereafter, I'm going to represent B star with this cartoon of myself where I am wearing a skirt and I'm spinning very rapidly. And this skirt forms around me a disk, which mimic the idea of this accretion disk, which is surrounding the B star. In the panel below here, you'll see how a BeXRB binary system usually looks. So you see that we have a B star, which is surrounded by this accretion disk that I mentioned, and which we detect from the infrared excess and emission lines. And this system usually is, the B star is usually in a system with a neutron star. Okay, so why are BeXRB binaries interesting? There are actually many reasons to be interested in this kind of systems, but in this talk, I'm going to mostly focus on what we can learn in terms of binary evolution. And also, we also quickly checked in this project what is the impact of BeXRB binary phase in terms of as possible progenitors of a neutron star black hole and neutron star system. And I can tell you already that most of the double neutron star system that we form, they go through a BeXRB binary-like phase. And there are other things for which this system are actually interested, among which we could actually learn something in terms of binary evolution that I'm not going to address here, but they are connected to the problem that and the challenges that I mentioned before. Another thing that I would like to mention here is this correlation that has been pointed out by Corbett in 1984. Between the orbital period and the spin period of the neutron star. So the orbital period is in the x-axis here, and the spin period of the neutron star in the BeXRB binary, you see it in the y-axis. And you see that there is this very nice correlation that I'm actually going to use later on in the talk. Okay. Another interesting things for which I will not have the time to focus much about, and I haven't really yet investigated with COMPASS, is this the presence of this bimodality in the spin period, which have been proposed to be generated by different supernovae by Knigna et al. In 2011. Okay, so BeXRB binaries have been seen in the Milky Way and in the Magellanic Clouds. But hereafter, I'm going to focus on the BeXRB binaries in the Small Magellanic Cloud, as in this way, I will not have to account for the effect of metallicity, for example, in the formation of this accretion disk. And in this way, I will also have a kind of homogeneous sample in this sense. Moreover, in this way, the sample that I'm going to look at is not really affected by the absorption in the galactic plane. The sample that I am specifically going to look at is the sample of the X-ray binary described in Coe and Kerr 2015. And I'm going to specifically going to focus on orbital period distribution, Bstar masses, and number of BeXRB binaries. So in this catalog, there are 69 BeXRB binaries, of which 44 have measured orbital period, which you see here the distribution of. And I am also going to focus on the Bstar masses, which, as you see here, as it is represented in this catalog, we have, they range from a value between 6 and 25 solar masses, which is slightly different compared to 3 and 25 solar masses that I mentioned before for describing Bstar population in general. So the question that we are trying to understand is, can we understand the main property of BeXRB binaries, these properties? And to answer these questions, we use the population synthesis code COMPASS, which for what concerns this topic, you can, in a certain sense, consider as a black box where you set some initial parameters and you, of course, give here some assumptions. And what COMPASS gives you is a population of evolved binaries. But as I promised before, I'm going to explain a couple of things about binary population and the assumption in COMPASS, which are assumed in COMPASS. Okay, so with COMPASS, we want to evolve binaries, and we start with 2 stars in a binary starting their life, which starts their life when both start to burn hydrogen in their core at the same time, and this moment is called the zero age main sequence. And at this moment, I define what is the primary and the secondary in terms of the mass of the components of the binary. So hereafter, when I say the primary, I mean the mass, the star which has which is the most massive at zero age main sequence. And when I speak about the secondary, I speak about the star which is the least massive at zero age main sequence, so at the birth of the binary. And something that we should take into account to understand and place the result of this work is that in COMPASS, we are not modeling the spins of these 2 stars and the evolution of their spins. Moreover, we also assume that the eccentricity here is 0 before the first supernova, and for what concerns our project, we also consider a fixed metallicity, which is roughly 1/5 of the solar ones, which roughly correspond to the Small Magellanic Cloud metallicity. So in turn, this means that we define the evolution of a binary from their initial masses and separations, again, having fixed the metallicity. Okay. So the second ingredient that I mentioned that is quite important to understand binary evolution in COMPASS is mass transfer. So we start with a 2 main sequence star in a binary, and the primary will evolve faster and so expand, and it may, if the separation allows, expand enough to overflow its Röhrsloop. The Röhrsloop is the region around the star where the matter is gravitationally bounded to the star. So as soon as the expansion goes outside this Röhrsloop, then mass is not gravitationally bonded anymore to the primary. And the 2 things can happen to the mass that is therefore lost by the primary, or it can be accreted by the accretor, or it will be lost by the binary. And this, what happens actually depends on the type of mass transfer, and in COMPASS we model mass transfer in 2 different ways. So we can have stable mass transfer or unstable mass transfer. In both cases, the donor, in our case the primary, will lose the entire hydrogen envelope unless the donor is a main sequence or a helium main sequence star. And but only in the case of stable mass transfer, some of this hydrogen envelope can have the possibility of actually being accreted by the secondary. Indeed, for unstable mass transfer, which we assume leads to common envelope, we know that the time scale involved are too short for the accretor to actually accrete a considerable amount of mass. So we just assume it doesn't accrete any mass at all. So what happens after the mass transfer is that we have a binary which is composed by a strip star. And depending on the type of mass transfer it experienced, so yeah, it can widen if it was stable, or it can shrink if it was unstable. And specifically, so if the mass transfer was stable, the primary will be in a system with a secondary which likely had increased its mass compared to before the mass transfer. And which is, and the binary itself is going to probably be wider compared to what it was before the mass transfer. If instead the binary experienced unstable mass transfer, this mass transfer often will lead to mergers. And if it doesn't, the binary will be quite shrink. And the secondary mass will probably be very similar to what it was before the mass transfer. As I mentioned before, no mass is assumed to be accreted during this unstable mass transfer. Okay, so the last ingredient that I want to mention is supernovae. So as you know, if there is a star which is massive enough, it will lead to a supernovae explosion. And for what concerns this project, we are interested to those supernovae explosions that generate a neutron star. And so the classical ones are core collapse and electron capture supernovae. We assume that the core collapse has a large kick, and usually the core collapse is the one that is associated to the higher mass progenitors, while the electron capture supernova is associated to the lowest and so the least massive star that can still generate a neutron star are usually going through electron capture supernovae. And in this case, we associate the newly born neutron star with small kick. If we account for binary, that not only will change exactly the range of when these two supernova will occur, but will also may also introduce a different type, a third type of supernovae, ultrastrip supernovae. Also in this case, we assume that the neutron star, which is born by ultrastrip supernovae, will experience a small kick. And ultrastrip supernovae actually come from ultrastrip progenitors. Ultrastrip stars are those stars that have experienced, in COMPASS, have experienced 2 mass transfer. The first mass transfer where they lost the entire hydrogen envelope, and the second mass transfer where they lost the helium envelope. Okay, so what we are trying to do with COMPASS is now to try to understand how do we get from a binary of 2 main sequence star to our Be Xray binary-like system that we observe today, where we have a neutron star in a system with a main sequence star which is rapidly rotating and with this accretion disk. So we have the possibility of going straight there without no interaction between the 2 stars, and other possibilities are instead these 2 stars interact, and the primary will start a mass transfer episode, which could be stable or unstable, and that is what we want to know. And later on, the primary may or may not go through again a second mass transfer before end up again impossibly having Be Xray binary-like systems. So to reiterate, this is the phase that we observe today. This is so where we have a neutron star which is emitting X-ray because it is accreting from the decretion disk of the Bstar. While what we want to explore with COMPASS is actually their evolution from zero-age main sequence. So we want to understand how do we arrive to Be Xray binary-like system. Do we need an interaction or don't we need it? And how would the interaction look like? Okay, let's now go back to our main story. So how do we select Be Xray binaries from our population of evolved binaries that is given to us by COMPASS? So we look at all the binaries and we say, okay, we just select the binaries which have a main sequence star, and specifically a main sequence star which has a mass above 3 solar masses, which roughly represent the OB spectral type that is typical of Bstars. Then we also ask that the companion to this main sequence star is a neutron star, and that actually the binary after is still a binary after the neutron star was born, so the binary has survived the kicks connected to the neutron star. And finally, the last requirement for our Be Xray binaries is that main sequence star now at this moment, at the moment of Be Xray binary, so at the moment of main sequence plus neutron star, is not Roche-Lobe overflowing into the neutron star. Main sequence, not Roche-Lobe overflowing into the neutron star. Okay, but in all this definition, we need to account that we need to remember when we look at our results that we are not really modeling the decretion disk, neither the selection effects. Okay, now the last thing that we need to account for to start actually comparing predicted and observed distribution of property of Be Xray binaries is to account for the star formation rate of the Small Magellanic Cloud. And this is how we do it. So here I'm plot the time axis. So we have 0 is today, and we go back into the past. This green line here is the star formation rate of the SMC following this this timeline. And what we do is we take all the systems that we have selected before with our 3 criteria, and we assign to each of them a weight which depends on the moment at which each binary was born, counting backwards. So substantially, what you see here in purple is the distribution of the time that it takes for our population of synthetic Be Xray binaries to go from zero-age main sequence to Be Xray binary phase. And so for each of the binary that we have selected, we look at what is the correspondence time star formation rate, and we use it to weight our binary. So now we can finally go to the results. And let's start with the formation channel. Okay, so we are going to describe the formation channel, specifically paying attention at the first episode of mass transfer. And we are going to say something on these 3 possibilities for the first stable mass transfer. So the first stable mass transfer might not even occur if we have non-interacting binaries. So we are going to check if this is a possibility to create Be Xray binaries, or the first stable mass transfer can be stable or unstable, or both. That can both give rise to Be Xray binary-like phase, right? Okay, so here I plot the orbital distribution of the Be Xray binary system, which are in the catalog of Coe and Kirk. And let me now show you what we see if we also plot the non-interacting Be Xray binary-like system. So these are systems which fulfill our 3 criteria for being called Be Xray binary-like system, but they go directly from Roslob to from main sequence, and they evolve as single stars, and until they arrive to a neutron star plus main sequence system. And we see that this binary will not contribute to our observed distribution. This doesn't mean they are not Be Xray binaries, but because we know that here is actually a region in the orbital period space where selectional effects are quite strong in place, it just means that this non-interacting Be Xray binary-like system for sure are not a significant part of the observed Be Xray binaries. So we are not looking at them, and instead what we are saying is that the first mass transfer, there has to be a mass transfer, and therefore the possibility is the mass transfer can be stable or unstable. And I'm going to argue that, as I'll show you later on, that it's more likely that the first mass transfer will be stable. So let's review what this means in terms of, indeed, again, formation channel for these Be Xray binary-like systems. So we start with zero-age main sequence. So at the birth of the binary with 2 main sequence stars, the primary evolves, it expands and fills its Roslob. In this way, it starts an episode of stable mass transfer, where the donor will give actually some mass to the accretor. So the accretor will accrete some mass, and this mass will span up the star and so generate a Bstar. And after this first mass transfer, what we are left with is a strip star in a system with a Bstar. And so for people of the field that know it, this, for example, is one of the possible interpretation of the LB1 system. Okay, then further evolution may happen and may also lead to a second mass transfer, but the important thing is that at the end, the primary will explode with a supernova and will leave behind, a neutron star in a system with a rapidly rotating main sequence star. And this is not a new proposed channel, and indeed, this is in agreement with some past literature too. But one thing that you should definitely take away is that this stable mass transfer is really important. And so let's have a look at what are the main parameters that, at least in COMPASS, are used to describe this mass transfer. So one of the main parameters, as I mentioned at the beginning, that is used to describe stable mass transfer in population synthesis code is the accretion efficiency beta, which represents the fraction of the mass which is lost by the donor and it is accreted by the accretor. Let's have a quick look at what are the common recipes for calculating this accretion efficiency. So we are going to look at the our fiducial accretion efficiency, which describes these beta parameters in terms of the property of the binary components. Then we are going to look at, so we have another common way to calculate beta is to fixing it to be 50% conservative. So only half of, only half of the mass which is lost by the primary is accreted by the secondary or by the accretor more in general. And we also have, we are also going to look at fully conservative mass transfer where the entire mass is accreted by the accreted, entire mass which is lost by the donor. And again, our fiducial case is considering beta calculated from the property of the binary components. The second parameter which describes stable mass transfer is gamma, which is defined as a ratio between the specific angular momentum of the matter which leaves the binary and the specific angular momentum of the binary itself. There are usually 3 different scenarios that are considered in this case. So we have isotropic re-emission, where the matter is assumed to be leaving the binary from the surface of the accretor. We have, and this is also our default case. We have also another frequently used scenario is a circumbinary ring, where matter leaves the binary from a circumbinary ring, which is roughly twice the separation of the binary itself. And finally, we have the fast or Jeans mode, where the matter is supposed to leave the system from the surface of the donor. Okay, now that we have learned some things about stable mass transfer in general, let's have a look at our results. So Bstar muscle, let's see how are we doing? So again, this is the problem that we are trying to understand. So Bstar in general ranges between 3 to 25, say 30 solar masses. You see solar masses are in the x-axis here, while Bstar in BeXRay binary ranges between, say, 6 and 25 solar masses again. So we are trying to understand if our binary population synthesis code can help us understanding why there is this gap. And if I just evolve my synthetic binary, BeXRay binary system from our default assumptions, this is what I'm getting. So focus on the pink line. The pink line is the mass of the main sequence star distribution. If we assume our fiducial configuration, and you see it peaks well outside the observed range. And here I'm also plotting the distribution of main sequence masses in the case of unstable mass transfer as for mass transfer. I remind you that we have said that this is not the way we are going to go, and now I'm going to argue why. Okay, so in both the cases, we have this peak of the distribution, which is well outside the observed range in BeXRay binaries. So we have two options to try to match observations, or we find a way to decide why this mass should not contribute to our population of BeXRay binaries, or we try to move these peaks towards higher masses. And to move this, it means increasing the accretion efficiency parameter, which, as I told you before, it makes sense only if the mass transfer is stable, because during unstable mass transfer, the time scale is so short that we assume that no mass is accreted during, or for sure is physically motivated the assumption that no mass or not a considerable mass is accreted during common envelope phases. Okay, so again, now let's review what are the, let's have a look to try to see which diet better fits our Bstar. Just a quick review. We have our fiducial prescription to define beta, dependent on the property of the components of the binary, and the two fixed at 50% and fully conservative. And here are the results. So here in the x-axis, again, there are the main sequence masses in BeXRay binary-like systems. And you see here that our fiducial, in our fiducial case, again, we have this distribution which peaks at much lower masses compared to the observed range. While if we go towards increasing accretion efficiency, going from 50%, 75% to fully conservative mass transfer, we move this curve towards higher masses. However, you can also see that the area below each of the curve actually keeps shrinking while while increasing this beta parameter. And for this reason, for this reason, substantially we pick our preferred model to be a 50% conservative, because this is the only model here which actually fits also the number of BeXRay binary system that we have in our catalog. I here also plotted like another curve which has a high angular momentum loss. Indeed, high angular momentum losses have been proposed, for example, by Portuguese Fart to explain the high masses of Bstar in BeXRB binaries. But we see that if we now use this kind of prescription, we do not have enough system left to match the observed number of BeXRB binary in the catalog. So the change in the accretion efficiency parameter is the way to go. Let's now have a look at the orbital period distribution. So again, here I'm plotting our results for the fiducial case. X-axis are log of orbital period distribution measured in days. The dark gray here represent the observations. So these are the orbital period of the 44 systems which have measured orbital period in the catalog, while the light gray area here are the remaining system, which we estimate the orbital period from the Corbett relation that I mentioned at the very beginning. And you see that if we compare observation with prediction, we do have a couple of big issues. So let's have a look at the system at large orbital period. And you see that in this case, we can actually explain this this difference by qualitatively from accounting for selection effects. On the other side, instead, selection effects cannot really, at least the ones that we could think of, cannot really explain why we should not see that many systems at such low orbital period. So that is more our problem. And now the question that we ask ourselves is this change on the accretion efficiency already fixing this problem we are having? And well, luckily, yes. So here again is our preferred model. And you see the orbital period distribution in this case. And this roughly matches the number and the observation of the observed population of BeXRay binaries. And here, maybe you can see even better than before that instead, if I would choose the conservative mass transfer, I would predict much less system compared to what we expect. Let's now have a look as last point in the results on what is the effect of changing the other parameter that enters in stable mass transfer, which is this gamma parameter, which describes the angular momentum loss during mass transfer. And okay, so here again, we have the orbital period distribution of the observed binaries, BeXRay binaries. And the purple line here describes our preferred model, where we again use the isotropic re-emission assumption, where we assume that the matter leaves from the surface of the accretor. And we are now going to explore, for example, let's have a look at the we are now going to explore two different gamma values and gamma angular momentum loss scenarios. So if I'm looking at the orange line here, this is for the circumbinary ring case. And you see that in this case, we predict to have a much, orbital period of picking up much shorter period compared to the observed populations. And not only so we have this overabundance at short period, we also lack of the bulk of the system that we observe. For what concern instead, if we look at the genes mode, you can see that we have this excess again at short orbital period. And for this reason, and I connected also further proof, let's say, from studying on double neutron star system, we say also this one is probably discarded. And I'm saying probably because, at least for what concerns this study, the presence of a peak of this peak at short orbital period is very much linked to our treatment of ultra strip supernova and stability criteria. Okay, and yeah, so let me just quickly summarize what are the main takeaway messages here. So the implication of these studies is that the accretion efficiency should be above 0.3 solar masses. Okay, so we actually said that our preferred model has an accretion efficiency we've set it to be fixed at 50%, but of course that is not a physical assumption. This is it was so more realistically what we can say it's what this study is saying us is that in general our accretion efficiency during stable mass transfer should be relatively high, should be above 0.3 most of the time. Another thing that, and this is actually interesting, by the way, because not only it has been confirmed by other studies, but recently an article appeared on arXiv saying actually finding the same thing, but instead of looking at BeXRay binary, they were looking at population of binary black holes found through gravitational waves. The other implications from this study is that we actually can explain the occurrence of a BeXRay binary in the star just by using the star formation ray burst in the Small Magellanic Cloud. However, this is true only if we assume that most of the main sequence stars that are in binaries with a neutron star are actually Bstar, or at least all of them which are, say, below in system below 500 days in orbital period, and should also stay Bstar throughout the rest of their life. Yeah, this is quite an assumption, and which we did kind of double checked, and it definitely can be related to the low metallicity environment to the SMC, which helps this star to live longer. Another thing that we can deduce from the BeXRay binaries, from this BeXRay binary study, is that the BeXRay binary sample in the SMC, for what concern system below 500 days in orbital period, should be close to complete. Of course, there are quite some caveats that we need to take into account. For example, like affecting the number of BeXRay binaries, also the number that we should assume to be BeXRay binaries. Moreover, meaning that there are some high mass X-ray binaries which have been detected in the SMC, which have not yet been identified as BeXRay binary, what they might very well be. Moreover, we should have a look and try to understand what we can learn from the missing BeXRay binary, a short orbital period. As I mentioned later at the end of the talk, this is connected to treatment of ultra-strip supernovae and stability criteria. And in this study, we also highlight where observation should and could go to help us constraining our beliefs on binary evolution, and specifically our assumption on the evolution of towards BeXRay binaries. And actually, there are quite some more things that we could learn hopefully in the future with studies, and they are related to what we have been looking at. And yeah, so for example, as I mentioned at the beginning, the formation, so BeXRay binaries can be related to the formation of double compact object, and indeed we do see that at least in our simulation, which only concern Small Magellanic Cloud metallicity, but we do see that the BeXRay binary are a big part of, that the double neutron star system, most of them go through a phase which is a BeXRay binary-like. And just reiterating that despite we have many buttons available, using population synthesis code to match observations and prediction, it's still useful and we can still learn a lot. And yeah, so I finish the talk with the final remarks here. Thank you for your attention.